Hi everyone, my name is Manel Rodriguez-Soto. I'm a PhD student at IIIA at Barcelona, and now I'm going to present you the paper Building Multi-Agent Environments with Theoretical Guarantees on the Learning of Ethical Policies, which I have written together with my supervisors Juan Antonio Rodríguez Aguilar and Maite López Sánchez. So, to begin with, we all have seen how the current advancements in AI are showing very impressive results each year. Every year, they can deal with more complex tasks and being more integrated within human societies. However, for them to fully integrate in human societies, we need to guarantee that agents learn to behave ethically, that is, in alignment with moral values. This well-known problem in the artificial intelligence community has received the name of the value alignment problem. A common approach to tackle it is to apply reinforcement learning so the agent learns what is ethical by trial and error. In more detail, this approach consists in designing an environment that incentivizes ethical behaviors by means of some exogenous reward function. The problem is that these incentives are chosen with a lack of theoretical guarantees, so we cannot know for certain if agents will learn to behave ethically or not. So, this is our research question. How can we guarantee that all agents in a multi-agent system learn to behave ethically while still pursuing their respective individual objectives? And before we continue, let me show you an example to illustrate the main concepts of the paper. This example is called the public civility game, and in it, two agents need to move every day through a narrow path to their destination. We can express the individual objective of the agents as getting to the goal as fast as possible. But as we can see on the picture, the left agent finds a piece of garbage in its way. To promote a more civic society, we would like agents to act in accordance with the moral value of civility and so bring this piece of garbage to a bin. So we can express the ethical objective of the agents as promoting civility. For this example, we will assume that agents can perform three kinds of actions. Move towards the goal, and if the garbage is in front, like in the example for the left agent, then it can throw the garbage aside, which could hit the other agent, or bring the garbage to the bin if it is also in front of it. Each action has different consequences with respect to the two objectives, individual and ethical. The action of throwing the garbage promotes the individual objective since it allows the agent to get faster to its goal. But it demotes civility because it creates a dirtier society or even a dangerous society if the agent throws the piece of garbage to where the other agent is. Conversely, the action of bringing the garbage to the bin demotes the individual objective because it is the slowest option of the two. But it is also the best of the two options in terms of promoting civility because it guarantees a clean and safe street. This leads us to the following conclusion, that the public civility game as a value alignment problem illustrates a multi-objective and multi-agent decision-making problem, and thus any learning approach to tackle it requires the use of multi-objective, multi-agent reinforcement learning. In brief, our approach consists in designing an ethical environment that guarantees that all agents learn to behave ethically while pursuing their respective individual objectives. So in more detail, in order that agents learn to behave ethically, the first step is to properly model their environment as a multi-objective one with two objectives, the ethical objective and the individual objective of each agent. This way, we can aggregate the two rewards in a way that prioritizes the ethical objective to the individual one, and we give this process the name of the multi-agent ethical embedding process. Then, if agents learn in an ethical environment with such ethical embedding, they will learn a joint behavior that prioritizes the ethical objective to the individual objective of each agent. Also, notice that by making this new ethical environment a single objective one, we are simplifying the learning process of the agents. And let me quickly emphasize on this. The agent's only work is to learn in the ethical single objective environment, and on the other hand, the embedding process is the task of the environment designer. So in summary, we provide our solution by means of the following two contributions. First, we provide the theoretical means to design a learning environment wherein ethical behavior is guaranteed. And then we also provide a process for automating the configuration of the learning environment. Now I will start by explaining the first point, the theoretical means. Here, the first step is to formalize the ethical embedding problem, which is the problem of creating an ethical environment for agents. So we start by modeling the ethical objective and the individual objective as the two reward functions of each agent in a multi-objective Markov game. We will refer to this kind of multi-objective Markov game as an ethical MOMG, which has an individual reward function R0 and an ethical reward function RE. And before we continue, in case any of you is not familiar with multi-objective Markov games, they are simply a generalization of Markov games that instead of having a scalar reward function for each agent, they have a vectorial reward function per agent, and consequently, the value function of each agent is also expressed as a vector, and these are all the differences with respect to single objective Markov games. And it is also worth mentioning that a multi-objective Markov game with a single agent is simply called a multi-objective Markov decision process, MOMDP. Back again with ethical MOMGs, having defined them, we can also formalize the concept of what is an ethical behavior in a multi-agent system. For it, we make use of the concept of Nash equilibrium. We will consider that agents are behaving ethically if their joint policies form a Nash equilibrium with respect to the ethical objective. And we define such joint policy as an ethical equilibrium. And here at the right, you can see a Venn diagram showing how ethical equilibria are a subset of all joint policies. And while this definition is very helpful, we still need more. As I said before, we need that agents learn to behave ethically while still pursuing their individual objectives. For that reason, we define a special subset of ethical equilibria, which we call best ethical equilibria. An ethical equilibrium is best ethical if also each agent is maximizing its individual rewards, subject to following an ethical policy. A best ethical equilibrium is the kind of joint policy that agents should learn. But how can we create an ethical environment in which agents learn such equilibrium? And recall that we wanted to create a single objective environment. Well, for that, the classical option in multi-objective reinforcement learning is to use a scalarization function. As its name implies, a scalarization function transforms the vectorial rewards of a multi-objective environment into the scalar rewards of a single objective environment. The most typical option is to apply a linear scalarization function that computes a weighted sum of the different objectives. So for instance, in the case of ethical MOMGs, this is how a linear scalarization function would look like. A weighted sum of the ethical objective and the individual objective of each agent. Here, f is the scalarization function, and the superindex I refers to each agent I, and the weights are W0, which is the individual weight, and WE, which is the ethical weight. In this work, we also consider a linear scalarization function in order to design the ethical single objective environment. In our case, for simplicity, we fix the individual weight as 1. Therefore, the work of the environment designer, that is, us, will essentially consist of setting the appropriate ethical weight of the scalarization function that creates the desired ethical environment. Now we have all the theoretical means to formalize the multi-agent ethical embedding problem as follows. Given an ethical MOMG, how do we need to set the ethical weight to guarantee that in the designed single objective Markov game, all Nash equilibria are best ethical? So this is the ethical embedding problem. And here you have a graphical representation of the problem with Venn diagrams. At the left, you can see the subset of best ethical equilibria of an ethical MOMG. And what we want to do is to design an ethical embedding that guarantees that the set of Nash equilibria in the single objective environment corresponds with the set of best ethical equilibria. And moreover, we assume that incentivizing the agents to behave ethically has a cost for the environment designer. And for that reason, we want to obtain the minimal value of the ethical weight that allows the ethical embedding. The good news is that we know that it is possible to find such ethical weight thanks to the following existence theorem, which is also one of the main results of our work. Given an ethical MOMG, there exists an ethical weight for which all Nash equilibria in the scalarized MOMG by such ethical weight are also best ethical equilibria in the ethical MOMG. And of course, this is given the appropriate extra assumptions. Please check the file paper for details. With this result, we can finally proceed to solve the ethical embedding problem. Our proposal to solve it is a two-step process that obtains the desired ethical environment in which agents learn to behave ethically. And as mentioned before, our process consists in designing an ethical environment directly from computing the appropriate minimal ethical weight. You will see that the main concept for computing each of the two steps of our solution is to decompose the MOMG into several MOMDPs, one per agent, then solve locally each MOMDP, and finally join the resulting solutions into the ethical MOMG. So we start with the first step, which consists on computing a reference ethical equilibrium that will be used in the second step to compute the solution ethical weight. To find this ethical equilibrium, we resort to first decomposing the ethical MOMG into several ethical MOMDPs, one per agent. We do so by fixing for each agent the policy of the rest with a random joint policy. Afterwards, we can compute the ethical policy of each agent by solving each MOMDP separately. To compute these policies, we can use any single agent reinforcement learning algorithm with a lexicographic ordering. Then we join all the computed policies to obtain the desired ethical equilibrium. And with this, we have finished the first step of our process, the ethical equilibrium computation. Now we make use of the ethical equilibrium to decompose again the ethical MOMG into several ethical MOMDPs. This time we make use of the ethical equilibrium to fix the policy of each agent. In each ethical MOMDP, we apply the so-called single-agent ethical embedding process to obtain the ethical weight that incentivizes each agent to behave ethically. This embedding is an algorithm from our ISCAI paper from 2021. And finally, we join the results again by selecting the maximum ethical weight found as the solution weight for the ethical MOMG. In summary, our two-step process consists in two decompose-solve-join cycles. First, decompose the ethical MOMG into several MOMDPs and solve each one individually to find an ethical policy for each agent. Afterwards, join the resulting policies to create an ethical equilibrium. This completes the first step. Secondly, use this ethical equilibrium to decompose again the ethical MOMG into several MOMDPs. Then apply the single agent ethical embedding to each MOMDP to find the corresponding solution weight vector for each. And finally, join the results to select the maximum ethical weight among those found to create the desired ethical single objective environment. And thus, these two steps form what we call the multi-agent ethical embedding process. To finish, we conclude by summarizing the main contributions of this work. First, we make headway in tackling the problem of designing ethical environments by providing novel formal and algorithmic tools that build upon multi-objective, multi-agent reinforcement learning. Then we characterize the obtention of an ethical environment in a multi-agent system as a two-step process that generalizes the single-agent ethical embedding process from our previous ISCAI paper. We proceed by formalizing the multi-agent ethical embedding problem and theoretically prove the conditions under which it is solvable. Finally, our findings lead to a process for automating the design of a multi-agent ethical environment in which it will be in the best interest of all agents to behave ethically while pursuing their individual objectives. Also, we didn't have time in this presentation, but in the full paper, we empirically confirmed our theoretical results with the public security game example. And thank you very much for your attention.